Good afternoon. So today we will begin our fifth lecture in this series, and let me just begin by going over what we covered in the last class. So if we could go down to the pad, then I will quickly go over a summary of what we covered in the last class. So in the last class we discussed subgroups. So before I continued my discussion on subgroups, I gave you a further example of a group, that is the integers and modulo n under multiplication, and we saw that that forms a group, the non-zero integers when n is a prime. So that was our last example of a group. We went on to subgroups. Okay, remember subgroup is a subset of a group which forms a group on its own under the same operation. So we provided that definition. Then after the definition, we went on to talking about the trivial cases of a subgroup. Then we talked about how do you test for the presence of a subgroup without actually going through all the axioms of the group itself. We came up with a simple test, and then we simplified this further for the case of finite groups. We looked at some example subgroups, the subset of the integers modulo 6 that are even, and also the single parity check code. We saw that both of these are examples of subgroups. Then the next topic that we went on to talk about was equivalence relations, and on the topic of equivalence relations, we looked at how does one define an equivalence relation, and then we proved some properties. We talked about the fact that an equivalence relation, so this is a particular form of relation, has the property that it partitions a set into equivalence classes, meaning that the set is broken into collections of subsets which are disjoint. And then we actually gave an example of an equivalence relationship that arises from the presence of a subgroup within the group. Okay, so we looked at such an example, and so that is about where we were. Okay, so now having done this, let me also go ahead and tell you what our plan for the day is. So our plan for the day is to actually talk about cosets, rings and fields. So we look at equivalence classes defined via cosets. That is a continuation of what we were doing in the last lecture. Then we'll look at some examples, and we'll also give some structure to the nature of the equivalence class in this case. We'll prove a further property, and then after that, so we started out by talking about groups and subgroups. So now we are going to keep going with our mathematical preliminaries, meaning that we'll look at some other algebraic structures before getting back to coding theory. So we'll actually talk about rings and fields, and these are algebraic properties that go in some sense beyond those of the properties of a group. We look at the axioms that go into making up a ring. We'll talk about the different types of rings. We'll end up with fields, and then time permitting we'll move on to talking about vector spaces, right. So vector spaces would take us into the realm of linear algebra, but that's only if time permits, right. So let's go back now, and I'll take you back to the lecture notes of last time. So let's just scroll through that. So we talked about subgroups and equivalence relationships. We said that you don't have to test for all the axioms. we looked at some trivial examples of subgroups, that is the group itself and then the subgroup that consists of a single element, namely the identity element. These are called the trivial subgroups. Testing for a subgroup, you can actually test brute force by checking all the axioms, but instead of that there is a simplified test in which you just simply check that if A, B are elements in H, then A, B inverse is in H. So, and then we proved by showing that this was equivalent to testing all the axioms. This further reduces in the case of a finite subgroup to just testing for closure, namely that if A and B are in H, that their product also is in H. It simplifies to that in this case. Then we began our journey into equivalence relationships. We defined what it meant to be a relation first of all, and then within the class of relations we pointed out what an equivalence relation was. It satisfies the properties of being reflexive, symmetry and transitive. Then the set of all elements that are equivalent to a certain element, let us say A, we call that E sub A, and we showed that these sets have the property that they are either identical for different elements A and B or else they are disjoint. Okay. And we gave a proof of that. Then we talked about the cosets of a subgroup. Okay. Then so we are in the setting where there is a group and there is a subgroup, and we are defining an equivalent relationship in a manner that involves a subgroup. The equivalence relationship was this, that is A is equivalent to B if AB inverse is in H, alright, and we verified that it is an equivalence relation, and that is about where we were. So, we will continue from that point onwards. So, let me begin now by putting down the title. So, first a quick word about equivalence relations. We saw last time that an equivalence relation partitions the set. That is that if you have a set S and then partitions it into subsets which are of the form EA, EB, EC, ED and so on. Okay. So, that was what we meant when we were saying that any two equivalence classes are either the same or they are disjoint. So, if you take the disjoint ones, then they partition the set. Then we were looking at the equivalence relationship that arises from a subgroup. Okay. So, we defined it. So, we had a group. So, this was a group, and then we had a subgroup, and we defined an equivalence relationship on the group by saying that A, B, if A, B are in G, then A is equivalent to B if A, B inverse is in H, and saw last time that this is an equivalence relationship. So let's try to get a slightly better feel for what the equivalence classes are. We do know from the fact that it's an equivalence relationship that the following picture holds, that you have G and you have some equivalence classes. So the question is, what exactly are these equivalence classes? So for that, what we're going to do is we're going to write down this this expression AB inverse is in H in a slightly different fashion. AB inverse is in H implies that AB inverse is equal to H for some element H in H, which implies that A is equal to HB, HB for some H in H. So therefore A is equivalent to B if and only if A belongs to HB, where we define HB to be the set of all elements of the form H times B, where H itself is in H. So in other words, therefore, the equivalence class of B now looks like H times B in this case. So just to get a feel for this, let's look at some examples. If you take G to be the integers mod 6 under addition, and if you take the subgroup to be 0 to 4 under addition, so you can verify that this is a subgroup. I leave that as an exercise to you. Okay, so now the question is, what are the equivalence classes that arise from saying that A is equivalent to B if and only if A B inverse is an element of H. So we've already seen that the equivalence classes are all of the form H B, which in the present context, since our operation is addition, means H plus B. So all the equivalence classes are obtained by adding some element to the subgroup. So since H is the set 0 to 4, you might think of this as the even subset of the integers mod 6. Then you can actually say that after all, if you set B equal to 0, that this implies that H plus B is H itself. So one of the equivalence classes is H itself. If you set B equal to 1, then H plus 1, remember that this is the set of all elements of the form H plus 1, where H belongs to H. So this is nothing but the set 1, 3, 5, you might think of this as the odd subset. So we started out with one equivalence class being H itself, which is the even subset, and another equivalence class being the odd subset. But these two partition it, these two partition the group. So we have the following picture, namely that if you look at the integers mod, this is Z6, then on the one side you have the 0, 2, 4, and on the other side you have 1, 3, 5. So these are the only two equivalence classes into which the group is partitioned. Why are there no more? Because if there was a further equivalence class, it must contain some element of Z, which means that it either contains an element in 0, 2, 4 or 1, 3, 5. But either way, if it contains 0, then it coincides with the equivalence class of 0. If it contains, let us say 3, then it must coincide with the equivalence class of 3. So these are the only two equivalence classes. Okay. Alright, so that is one example. Now let us look at a second example. So this is the example of partitioning into equivalence classes. So this time let us take G let us take G to be the set of all 7 tuples under modulo 2 addition, and let us take H to be a code C plus, where C is the even parity code. We also call this the single parity check code. And we know that this is a subgroup, because this showed up earlier when we were checking for a subgroup. So now, so the cosets, you can verify that in this case what happens is that the set of all 7 tuples once again is partitioned into 2 classes. One is the code and the second is the code plus any vector of odd Hamming weight. In particular, I can take 0, 0, 0, 0, 0, 0, 1. And so basically what we have here are the even parity vectors, and on this side we have the odd parity. And the reason why all the even parity vectors fall into one equivalence class is simply because their difference also has even parity, which means their difference belongs to H. Okay. So I will leave it to you to fill in the details. So we will just leave it at that in the interest of moving along. So verify that this is the case. right. So that with that we are done with the examples. Now, one other property that we will actually use a little later is that when you look at the equivalence classes that arise from the presence of a subgroup within a group, that the number of elements in each equivalence class is the same. Okay. So, let us go ahead and show that. So, we will put this down as a claim. Let G be a group be a subgroup let A equivalent to B if and only if AB inverse is in H. Then there is a one-to-one correspondence between the elements of different different equivalence classes. In particular, when H is a finite subgroup, and this will always be the case in coding theory. So, when I say that a subgroup is finite, we simply mean that the size of the subgroup is finite, and in all of our theory of error correcting codes, we will always be dealing with finite subgroups. So, in particular, when H is a finite subgroup, any two equivalence classes are of the same size. Okay, so this is our claim. So, the claim is that there is a one-to-one correspondence between the elements of the equivalence classes. Now, we know, so the proof. So, the proof of a claim, we know that all equivalence classes are of the form H plus B for some B in G. So, let H plus A and H plus B be two distinct equivalence classes. Okay, so we have, so what we want to show is that there is an equivalence relationship that there is a one-to-one correspondence between the elements of these two equivalence classes. So, if this is if this is H plus A, and if this is H plus B, we want to show that for every element in here, you can actually map to a unique element in here. So, there is this very nice and simple picture in this situation. So, let us call this mapping phi. So, there is a mapping phi which is both one-to-one and onto. Okay. So, the question is to actually prove this, we just have to show that there is a mapping which is one-to-one and onto. So, what is that mapping? Phi, we define phi via phi of A plus H. Okay, so maybe to be careful, since it's H plus A, let me be careful and write this as H plus A. So, this is phi of H plus A. If the group was commutative, then H plus A is the same as A plus H, but let us say we don't know that, although in the applications to coding theory it will be commutative. So, phi of H plus A will be H plus B for all H in H. Now, clearly this is onto. Phi is onto, because what does onto mean? Onto means that we just have to show that onto simply means we have to show that that for every element on the right hand side, there is a corresponding element on the left which phi takes and maps onto that element. Okay. But if you go down to the picture here, it's clear that if you want to find what, let us say that there is a particular element here which is H plus B, let us say this is H prime plus B. To find out which elements go here, all that you have to do is you have to take H plus A and H prime plus A. So, there is no problem showing that the map is actually onto. So, now the question is, how do you show that it is one-to-one? So, the worry is maybe phi of H plus A and phi of H prime plus A will map to the same element. To show one-to-one, assume to the contrary that phi of H1 plus A is equal to phi of H2 plus A, i.e. H1 plus B is equal to H2 plus B. But since I can simply cancel B on both sides, implies by cancellation, which strictly speaking means that we are going to add B inverse or minus B on both sides, that implies through cancellation that H1 equals H2. Therefore, yes?
No, sir, carry on.
Therefore, H1 plus A is equal to H1 plus is equal to H2, H2 plus A. Therefore, the map is one-to-one. Okay. Now, I can understand that there will be a little feeling of impatience as you are watching through this, it seems like a lot of abstract math and you are not sure where you are going. So apart from asking you to be a little bit patient, I just want to tell you that we are just building up this simple picture in our minds, which basically is a generalization of what you saw in the example of the even parity code. There we saw that the whole set of all 7 tuples was partitioned into equivalence classes, and the equivalence classes were either the even parity or the odd parity, and of course the number of even parity vectors is equal to the number of odd parity vectors. Okay, and this similar situation is true in general. It may be that you will have more than 2 equivalence classes, and typically you will, but all equivalence classes are of the same size, and all equivalence classes are going to look like C plus something, and so the code itself will be one of the equivalence classes. So this example that we just saw is simple, but yet at the same time fairly representative. Okay. So we are done with equivalence classes for now. So now we'd like to move on to talking about a fresh, a new type of algebraic structure which is called a ring. Okay. So what is a ring? A ring is a set R together with 2 operations plus and dot. So you can think of these as addition and multiplication, respectively. So recall that when we were talking about groups, on the other hand, there was just a single operation, right? So there was just a single operations, and then there were axioms all related to that single axiom. Now for the first time we are actually talking about a set, but now there are 2 operations. Okay, so that's the difference. And so what we are going to do is we are going to lay down axioms involving both of the operations, satisfying the following. One, R plus is an abelian group under addition. Secondly, A B in R implies that A times B is in R, and you can say that this is the operation of closure under multiplication, closure under multiplication. Then after that you have the distributive laws. A times B plus C is equal to A times B plus A times C, and A plus B times C is A times C plus B times C. These are the distributive laws. Right? And the fourth property is that A times B times C is the same as A times B times C. So this is associativity under multiplication. So we have a total of 4 axioms. So the first one actually says, first one confines itself to just a single operation, that is addition. It says that if you take R and then if you take addition alone, then R plus must be an abelian group. And we know what that means. It must satisfy closure and addition. It must have an identity element. There must be an inverse. Addition is associative. And since it's abelian, addition is also commutative. So that single first property really is, can be expanded into 5 properties. But we've already studied that, so that we understand pretty well. So now we are introducing the second operation, which is multiplication, and then we are laying down some other rules that it must satisfy. Now, there are 3 other rules listed below, 2, 3 and 4. Of the 3, 2 pertain only to multiplication. So the 2 properties that pertain only to multiplication are closure under multiplication and associativity under multiplication. Okay, so these 2 must be satisfied. Now, if you're thinking in terms of a group under multiplication, I mean, if that was the goal, then in some sense you're satisfying 2 of the 4 properties, the other being identity and inverse. But in reality, we are not going towards the group, at least not yet. Okay, so we have 2 properties, that is closure and associativity under multiplication. The third property is the distributive law. So the distributive law is interesting for 2 reasons. First of all, it's interesting because it's an axiom that relates to both addition and multiplication. Okay, that's one reason why it's a little bit different from the others. But more interestingly, and also from an applications point of view, is that if you look at just this operation, A times B plus C, now think of it as a computation that you are performing. So on the right hand side, it says that A times B plus C is AB plus AC. Now if you had to carry out this computation along the lines of what the right hand side suggests, then the total number of operations would be 1 for multiplying A and B, 1 for multiplying A and C, and a third operation to add the 2. So that's a total of 3. On the other hand, if you actually look at the left hand side says there's a smarter way to do it, because I can actually take B and C and add them together and then multiply by A. So it says that instead of doing 3, you can actually do 2. Okay. Now nobody is impressed. They'll say, okay, what's the difference, 2 or 3? It doesn't really make a difference. But in practice, yes, there's a big difference, because it turns out that when you repeatedly apply this distributive law, you can save considerably in the number of operations. And in fact, it turns out that this simple distributive law is in a way behind the savings in computation afforded by simplified decoding algorithms for certain error, for a very important class of error correcting codes, actually 2 of them. One is the class of low density parity check codes and the second is turbo codes. But we'll come to those somewhere in the middle of this class. Okay. So anyway, so the axioms that make up a ring are that under addition it must be an abelian group, under multiplication it must be closed and associative, and then it must satisfy the distributive laws. So these are the axioms. Now I am what I am going to do is I am going to keep pushing the definitions a little bit further. Okay. And in the interest of keeping you motivated, I will give you a preview of where we are headed on this. So, where we are headed is the following. We want to organize the various types of rings that exist into a diagram of this form. Okay, so, what are at the corners of these? Well, at the very top you just have a ring, okay, a ring as we have defined it. Now, to this side we have a ring which is commutative. So, we have a commutative ring. On this side you have rings with identity. And then we have what is called an integral domain. Here we have division rings, and then at the bottom finally we have fields, a field. So, in some sense there is a progression of properties as you go from top to bottom, and there are in some sense you can progress from being a ring to becoming a field if you possess certain properties. Okay. So, and the way you should interpret this diagram is that start from the right fork, there is a ring, and if under multiplication if the ring is commutative, then we call it a commutative ring. If further it satisfies the property of having no zero divisors, so some of these points I will expand on in just a few minutes. So, apart from being commutative, if it further has the property that there are no zero divisors, then it is called an integral domain. Now, going down the other fork, if it is a ring with identity, so that means you are just adding the presence of an identity element. And now, as far as the division ring is concerned, if every non-zero element has an inverse, then we say that it is a division ring. And then in the end we have a field. So, what does a field have? Well, a field has the property, it has all of these properties, that is, it is a commutative ring, it is an integral domain, it is a ring with identity, it is a division ring. When it has all of these properties, it is called a field. Okay. And so, I am going to now take some few minutes to write this up, and then we will look at examples, some examples of rings, and then we will figure out where to place them on this chart. A commutative ring is a ring in which multiplication is commutative. i.e., A times B is equal to B times A for all A, B in the ring. So that's a commutative ring. Then a ring with identity is simply what it says, is a ring with multiplicative identity, which we will call 1. So here in the context of rings, the identity under addition will be called 0. So the identity under addition is written as 0. So what this actually means is that, so let's say, let's write this as IE A times 1 is A is equal to 1 times A. An integral domain is a commutative ring that has no 0 divisors, i.e. A times B equal to 0 for A, B in R if and only if A equal to 0 or B equal to 0. Of course, both can also be equal to 0, but at least one of them must be equal to 0. Now notice that an integral domain requires that the ring be commutative. Okay. So in a way, that is why we list it in this figure, we list it below. Okay. Here is the property of it being commutative, and below that we have the integral domain property. Okay. And finally, we have a field. We have yet another ring, a division ring is a ring with identity in which every non-zero element in R has a multiplicative inverse. i.e. A is in R and A not equal to 0 implies that A inverse implies that there exists an element A inverse in R such that A times A inverse is A inverse times A is equal to 1. Now, by the way, there is also an additive inverse. So, just as a short note, let me just point out that additive inverse of A is written as minus A. Okay, so the multiplicative inverse is written as A inverse, but the additive inverse is written as minus A. And finally, we have a field. A field is a commutative division ring. Which means that so let's which means that the following: it has identity, it is ring with 1, the non-zero elements have inverses, and it's commutative. So, as a result of this, we have that in a field implies that in a field F, we have the property that F plus is an abelian group and F star multiplication is also an abelian group. So, that means that in a field, so the field is an algebraic structure with a lot of algebraic object with a lot of structure, because under addition it is an abelian group. In some sense, with respect to addition, it has all the properties that you like, and it also has all the properties that you would like with respect to multiplication. Okay. But of course, just a note of caution, you cannot define a field just by saying that it is an abelian group under addition and the non-zeros under addition form an abelian group, because there are some axioms, additional axioms. For example, even without excluding 0, the set is closed under multiplication. Also, there are the distributive laws. Okay. So, field is more than that, but it is good to keep in mind that you have an abelian group, you have two abelian groups in some sense, one is under addition and the other is under multiplication. So, now let us go ahead and look at some examples and we will figure out where to put them. So, here, so examples of rings. So, first of all, let us look at the real numbers. Okay, so this is R. or the complex numbers. C, or the finite field zero one. You can readily check that all these are examples of fields. Okay. Now, what I have called here as 0, 1, I may not have referred to it as a field earlier, but this is the same set under the same set of operations that we carried out earlier, namely that 0 plus 1 is 1, 0 plus 0 is 0, 1 plus 0 equals 1, etc. Okay. So, under these same operations as seen earlier. Okay. So, these are all examples of fields. So, in the figure, we can actually go ahead and put these down here. So, R the complex numbers, F2, all of these are examples of fields. Okay. Now, what we will actually do in the next class is we will put down some other examples. I will close with one other example for today. The set of integers so since we are close to finishing time, perhaps I won't write it out, but I will just say it in words that with respect to this figure, the set of integers forms an integral domain, and that is the reason for its definition. Okay. But since our time is up, just to summarize, we looked at equivalence classes arising from a subgroup, okay, and we saw that they partition the group. We looked at examples, then we talked about different types of rings, and we finished defining them, and we were going to look at some examples. So, we will continue from this point onwards, right. So, thank you.